All right, our next speaker this afternoon is Ashley Carpenter, who joined us from UCLA, where she'll be a junior this coming fall. Ashley has been working with Ylva over the summer, and she'll tell us today about her project, Do the Cores of Massive Stars Spin Slow or Fast? First Measurements from Interacting Binary Stars. All right, go ahead whenever you're ready.
Thank you for the introduction. To start off, I want to give everyone some context on the theory of stellar evolution. So the majority of a star's life is spent burning hydrogen in the core. Towards the end of a massive star's life, it will expand, become a red giant, and then the core collapses into either a neutron star or a black hole. So one of the mysteries of stellar evolution has to do with how angular momentum is transported inside of stars. Young massive stars have been observed to rotate over a large range of speeds, reaching really, really high rotation rates, as shown here in a sample of hundreds of massive stars. Through gravitational wave events, black holes have, on the other hand, not been detected to spin rapidly. Here is one example of the spin detected in a binary black hole merger event, which is consistent with zero spin. So why are we looking at the rotational velocities of stars and comparing them to the spins of black holes? Well, we can't really measure the surface rotation of a black hole because they don't actually have surfaces. One way that we measure the spins of black hole mergers is by using gravitational wave detectors, with a spin of 1 corresponding to maximal high rotation rates and a spin of 0 corresponding to 0 rotation. So from a young massive star to a red supergiant to core collapse and then to a black hole, why are the spins so inconsistent with each other? What exactly happens between the beginning of a star's life and the end? How come black holes spin slow when their progenitors spin fast? Maybe all stars spin down with age, or maybe the cores of massive stars always spin slow. And these are ultimately the questions I've been aiming to answer this summer with my research. So normally we can't see what's going on inside of a star because it's surrounded by a thick hydrogen envelope. Here is an oversimplified view of the structure of a star. You have the helium core and you have the hydrogen envelope. But what if we were actually able to see inside of the star and analyze how fast the core is rotating? Well, luckily we can with strip stars. Strip stars are stars that have been stripped of their hydrogen envelope by a binary companion. Towards the end of a star's lifetime, it can expand, and if the massive star grows past a certain point, the outer envelope will feel a greater gravitational pull towards its companion, and it can lose its mass. What we have left is an exposed helium core, with which now we can take spectra. So with spectra, we can use the properties of rotational broadening to determine the speed of exposed helium cores. So how does this Doppler effect work? Essentially, you have light that you observe on the side of the star that's coming towards you, and those wavelengths get shorter and become blue shifted. And on the right side, the opposite happens. The light becomes red shifted. And so this simultaneous blue and red shifting of the light causes two things to happen to our spectral lines. They get broader and they become more shallow, less deep. So to demonstrate the effect of rotational broadening, this is an absorption line of highly ionized nitrogen that was observed in a 4 solar mass strip star in the Large Magellanic Cloud. And I will overlay models with different rotation rates. So starting with 0 kilometers per second, you can notice how as I increase the speed, the model changes, getting more shallow and broad. For this line, I want you to pay attention to which line you think may be the best fit. The higher I set the speed, the more the line becomes broad and the farther it gets from the data. So for a range of different spectral lines, I've been using this by eye fit method to understand the rotational velocity of this particular helium star. But to analyze a best fit more accurately, we turn to the chi-squared method, also known as the chi-squared test. It is essentially used to determine whether there's a statistically significant difference between the expected or modeled flux and the observed flux. So I created a Python program to essentially loop through different rotational velocity values between 0 and 200 kilometers per second. A lower chi-squared value meant a better fit, and therefore a lower chi value was preferred, which brings me to my next step, which was to minimize chi. So in this graph over here, you can see a plot of chi-squared over the rotational velocities for the nitrogen 54604 line. Using statistical methods, I was able to find upper limits for 1, 2, and 3 standard deviations from our best fit. And these upper limits give our results more confidence in how quickly or slowly the stars are spinning. So yeah, I mean, noticed how in this graph, I said to keep in mind which line you thought might look the closest, and we can see it's probably 0. But yeah, so we couldn't get an actual measurement. We had to take upper limits. So we calculated the upper limits for 9 different spectral lines for 1, 2, and 3 standard deviations from our best fit. And before we examine them, I'd like to emphasize that all of the data is consistent with 0 rotation. And so first here is our highly ionized nitrogen, of which the limits were just shown, as opposed to helium-2 4200. The upper limits are significantly higher. This line in particular was not very sensitive to rotational broadening, with a best fit of 0 kilometers per second and some pretty high upper limits. The third standard deviation was nearly 350, which isn't quite slow. So with an error that large, we can't really trust that line to give us a robust measurement. So just from looking at these 2 different spectral lines, you may be wondering why they produce such significantly different upper limits. Well, if you look at the spectral lines with the models side by side, you'll notice that the helium-2 line on the left is much less sensitive to the different rotational velocities when compared to the nitrogen. The helium line itself is already pretty broad, so it's pretty difficult to notice any significant differences between the lines. And here we have the upper limits for all 9 different spectral lines. We can see a range of different values for some lines being more sensitive than others. With nitrogen 5 as our most sensitive and reliable line, we think that the core of this particular star may be rotating slowly. And I would like to reiterate that we could not measure the actual velocity, but only get upper limits for this particular star. Even though I found a best fit rotational velocity, the data was consistent with 0 rotation. Most of our lines had a best fit of 0 or very close to 0. So taking upper limits gives us a more robust measurement for comparison. And with that in mind, we also have to consider extenuating factors such as mass loss rates, wind speeds, and temperatures, and how that may impact sensitivity of each spectral line to rotational broadening. So yeah, to give a brief summary of what has been done so far, I use rotational broadening to determine potential upper limits for the projected rotational velocity of a 4 solar mass star in the Magellanic Clouds. The main result now is that this intermediate mass strip star has a rotation rate consistent with 0, and further constraining the rotation rates of other exposed cores of massive stars will be important for understanding the core rotation. And so while preliminary rotation rates are slow per se, we cannot directly compare them to the low spin rates of black holes, since they are not exactly the same thing. I'm looking into converting our rotational velocities to spins to get a more accurate representation of what our data means. These results are promising in that they may help us solve the mystery of how spin evolves with time in the evolution of massive stars from birth to death. And with that, thank you all for listening. I would like to give a special thanks to my advisor, Ylva, and Gwen for running such a great CASSI program this summer. This has been a wonderful experience. Thank you all.
All right, beautiful presentation, Ashley. Do we have questions? So I'm curious, you have here on your slide that there are 8 additional stars, presumably strip stars, that you have spectra for that you could do this analysis. So I'm excited eventually to hear the results about that, but I'm curious also if you guys have talked at all about whether it's possible to find still more stars to do this kind of analysis on, or if 8 is kind of the limit of what we're likely to have anytime soon. I don't know if you guys have ever talked about that or not.
I'm not really sure about finding more anytime super soon, but I know that Beryl will talk more about looking for stars in different metallicity environments, so she may be able to clarify that a little better.
Perfect. All right, any other questions for Ashley? Josh.
Can you remind me which spectrograph the data you're working on are from, and whether it's possible to get higher resolution spectra?
I'm not sure what spectrograph it came from. I'll have to ask my advisor. But yeah, I think we are looking into getting better spectral resolution. I think our spectral resolution for our spectra right now is about, we can't measure more accurately than say 20 kilometers per second. But yeah, I think a better resolution would be more helpful.
Perfect. All right, if there are no other questions, let's thank Ashley again for her presentation.